Hello and happy weekend to my calculus rock stars, because that is exactly what you are. What I'd like you to do is to get out this piece of paper that I gave you in class today. And as you saw on the teacher page, I did attach several copies of this because I want you to make a couple of copies, particularly as we introduce ourselves to just a new perspective on relationships between two variables. Okay, what you're looking at here is polar graph paper, okay? And people often ask the question, isn't this just a unit circle? And the answer is not necessarily no. I mean, I guess one could look right here at this distance of 1 and say, well, at all these distances of 1 from the origin, couldn't this be a unit circle? And I guess that could be, yes. But generally speaking, the polar graph paper is just a graphing coordinate system, very much like the what's called a rectangular coordinate system, right, which we have used probably your entire mathematical life. This is called the Cartesian or the rectangular coordinate system, where we graph points in terms of x and y, right? This is some point x comma y, okay? So this is the Cartesian coordinate system or the rectangular coordinate system and the polar coordinate system. Now, what's particularly interesting is you can superimpose the two coordinate systems upon one another, and I'm going to do just that. You know, if you did this, superimpose the x-axis and the y-axis on the polar coordinate system, what you see here is that the x-axis could be thought of as this line that passes through the center of the circle horizontally, right? And the y-axis is here, and that is absolutely perfectly valid and fine. And in fact, in some places, it's actually convenient to define a point to have the two coordinate systems superimposed upon one another. All right. So let's talk about the basics of what a polar coordinate system is, how you go about graphing on polar graph paper, and how you talk about relationships between variables and how they manifest graphically in the coordinate system. And when we begin this, let's start at the very beginning. You know, when we talk about the Cartesian coordinate system and we talk about a point on the Cartesian coordinate system, we are so used to thinking about the fact that a point on the Cartesian coordinate system is described as the horizontal distance from the origin and the vertical distance from the origin, and this distance, x comma y, right? We almost could do this in our sleep. X is the horizontal, y is the vertical. It's like boop, boop, right? -1, 5, -7, -1. You can follow my pointer here. 3, -3. The point is, when we graph a point on the two-dimensional space defined by the coordinate system, we know that x and y are defined as such. Well, the polar coordinate system asks a different question. It asks this question. It says, can I describe a point from a different perspective? And, you know, one of the things that I talked about a great deal early on in the year, and then I think I tried to reinforce this over the course of the year, is different perspectives on a single thing inevitably allow you to do more with the thing that you're working with, right? So sure, it's fine and well to describe a point in terms of an x-coordinate and a y-coordinate, where the x-coordinate is defined as the horizontal distance from the origin, y is the vertical, right? Well, the polar coordinate system says, you know what? I could describe that point in terms of the following. The distance that point is from the origin, and let's call this point r, and the angle theta that r distance makes with the positive x-axis. Okay, so yes, it's always with respect to the positive x-axis. And if you're curious, you see this dark black line here? That's why it's dark black here, it's light black here. This is reinforcing the fact that the angle theta is always with respect to this axis. We call it the positive x-axis here. Here, this is often referred to as the polar axis. Okay, it's the polar axis. So the question is, couldn't I describe this point, which is described in the Cartesian perspective, through the Cartesian perspective as 4, 2, I can also describe this point as a point r, theta, where r is the actual distance from the origin and theta is the angle that radial distance makes, or that radial segment makes, with the positive x-axis. And let's have a conversation here about, if I know that x equals 4 and y equals 2, how can I find r? Well, hopefully you see here a right triangle. And you see here that x squared plus y squared equals r squared. And in fact, you know what, boys and girls? X squared plus y squared will always equal r squared, because you can craft here a right triangle. So if x is 4 and y is 2, I get 16 plus 4 equals r squared. So r equals the square root of 20. So this point here is the square root of 20, comma. Okay, what about theta? Well, theta, is an angle in a right triangle. So I could do any number of trig ratios, especially since I have the x length, the y length, and now the r length. But just for convenience, I'm going to do x and y. And we know that the tangent of theta is equal to 2 over 4, or 1/2. Now what I'd like you to do is to be in radians here, because as you can see, my polar graph paper happens to be in radians. Tan theta equals 1/2. Theta equals the inverse tan of 1/2. And using a calculator, I know that because 1/2 is not one of our conveniently memorized tangent values. I get an angle theta that is about, I have to go find my calculator and figure it out. Hang on a second, boys. Okay, I got 0.463 radians. So this point now, while I could call it the point 4, 2, I can also describe it with polar coordinates as the point radical 20, 0.463 radians. Okay, so that is just kind of a quick and dirty look at, just talking about a point that is radical 20 units from the origin that makes an angle of 0.463 radians. All right, so let's just practice a couple basics here. Here we have, again, this is the polar graph paper. Go ahead and just graph these points for me, please. Go ahead and graph point A. Let's call point A 2, pi over 4. Let's graph point B, and let's call point B, all right, let's call point B 3, 3 pi over 2. And then let's do something kind of weird. Let's do this. Let's call point C negative 2, pi over 3. And maybe you'll say, I wonder what negative 2 is. We'll just make a guess, and let's just see what happens. Okay, well, point A, the distance of 2 from the origin at an angle of pi over 4. Well, here is the angle pi over 4, and the distance of 2 is right here. So there is the point A at 2, pi over 4. B is 3, 3 pi over 2. Well, where's the angle 3 pi over 2? Right here, 1, 2, 3. Here we go, right here. Where is the point C? Well, C is at the angle pi over 3. Boom. Uh-oh, this is the angle pi over 3, and if I were to travel a positive radial distance toward pi over 3, I'd head this way. But a negative radial distance is going, let's see, pi over 3. Oh, negative is going to bring me down to here. Negative 1, negative 2. So right there. So R can be negative. R definitely can be negative. Okay? All right, now here's what I want you to do. Would you please go ahead and convert, let's convert point C, let's convert the point negative 2, pi over 3 into familiar rectangular coordinates. So you have it in terms of polar coordinates r, theta. Well, what are the rectangular coordinates going to be? And maybe because we're still new here, maybe you'll go over here and say, okay, maybe I'll take a look at this right triangle. Maybe I'll do this, right? Maybe I'll do this. Oh my, I'll do this and this, right? Make a little right triangle there. And I know this entire angle here is 4 pi over 3. but what really matters here is the reference angle, pi over 3, right? Okay, and I know that, let's see, the cosine of pi over 3 is going to equal, okay, this is the cos of pi over 3 is going to equal adjacent. Let me just draw this a little better here. Hang on a second, everyone. All right, let me go draw that again. Here we go. Here's the hypotenuse, and here is this, and here is this, right? Okay, and I know that this angle here is pi over 3, right? And I know the hypotenuse too, don't I? The hypotenuse has a length of 2, right? I know it's negative 2, but the actual hypotenuse length is 2. So the cos of pi over 3 equals, I'll call this x and I'll call this y, equals x over 2. So x equals 2 times cosine of pi over 3. Okay, and y will then equal 2 times the sine of pi over 3. Because you know that the sine of pi over 3, if you look at that purple right triangle, is going to equal opposite over hypotenuse. Well, look at this. This is beautiful because cos of pi over 3 and sine of pi over 3, I don't need a calculator. Cosine of pi over 3, let's see, who knows it? Cos of pi over 3 is a half, so x equals 1. And sine of pi over 3 is radical 3 over 2, so radical 3 is the y-coordinate, but we're in quadrant 3. So really I have to make the adjustment and say the point in question, that point negative 2 comma pi over 3 is equivalent to the point negative 1 comma negative root 3. All right. I'm going to highlight a couple of things here because sometimes keeping track of the negative, positive, all that can be a little bit difficult. But there are 3 relationships you're going to want to keep hold near and dear. X squared plus y squared equals r squared. The other equation you're going to have right here is, it's right here, look at this one. Sine of theta always equals x over r, r being this distance. I think I just pointed to cos and said sine. Cosine of theta always equals x over r. Sine of theta always equals y over r. So what that means is, in general, you know that the sine of theta will always equal the y-coordinate over the r, the radial distance from the center. Typically, you see this written as y equals r sine theta. Similarly, since the cosine of theta equals x over r, you know this is going to mean that x equals r cos theta. These 3 formulas are really helpful to just commit to memory because they'll just allow you to convert between coordinate systems. Now let me tell you what that means. Let's see over here. Like, let's say I didn't want to do this drawing at all, right? And let's say, like, you're wondering, could I use this shortcut with this point here? Like, we're working with point C. C is negative 2. Theta is pi over 3. Like, if I just use those conversions, will I be able to get the correct x and y coordinates without having to then kind of clumsily think about, okay, I'm in quadrant 3, that means this has to be negative and this has to be negative. So let's see. Well, here at point C, r equals negative 2, right? And theta equals pi over 3. And if I was wondering, well, how do I convert this point into rectangular coordinates? Ms. Yem told me I can just do x equals r times the cosine of pi over 3. And you will see here that if I do r equals cosine of pi over 3, I immediately just get negative 1 because this negative sign took care of it, right? Similarly, y equals negative 2 sine of pi over 3. Well, that will mean that y equals negative radical 3. So these conversions are great in that you can input in a negative r, you can input in whatever the angle theta is, and if you use these equations, it will take care of the positive and negative for you. Okay? All right, so that is just, you know, getting used to a different coordinate system, describing points in polar versus rectangular form. Let's talk about now just some simple curves, okay? Let's just talk about some simple curves. Let's see. I'm going to regraph the polar curve here, and maybe you're going to want to also get another coordinate system, another polar graph paper. Where'd it go? Hang on a second here. Okay, what do you think the graph of this would look like? If I said r equals 2, what does the graph of this look like? In other words, this is saying all points on this graph where r is 2. Well, I hope you say that r equals 2, just like when we were back in the world of the Cartesian coordinate system of x and y. When you saw the equation y equals -1, you hopefully learned, and I'm sure you did, that in this equation x is arbitrary. X can be anything as long as y equals -1. So y equals -1 ended up being a horizontal line at -1. Well, r equals 2 means theta is arbitrary. Theta can be anything as long as the points are a radial distance of 2 from the origin. So r equals 2 describes this circle right here. Oh, Amy. Oh my goodness. It's just wrong on so many levels. Let's see if I can do a better job than that. R equals 2. This is the graph of r equals 2. Okay, how about this? What's the graph of this one? What is the graph of, this is the graph of r equals 2. What does the graph of this look like? Ready? Theta equals 2 pi over 3. What does this look like? This means r can be anything as long as theta equals 2 pi over 3. Well, you know what that would look like? That would look like a line through the origin. In fact, it would look like this line. Here are all the r values that are positive when theta equals 2 pi over 3, but we know r could also be negative. So this here is the graph of theta equals 2 pi over 3. So right away we know that in the world of the polar coordinate system, r equals some constant describes a circle. I guess we could say it also could describe a point, right, if r equals 0. And then we also know that theta equals a constant, describes a line, not going to be very particular, describes a line through the origin, mind you. Okay, describes a line through the origin. Okay? All right, lovely. Let's do a graph that looks like this, and hopefully you are a little bit relaxed right now, and well, okay, maybe let's keep you in a relaxed state and let's just kind of sit here comfortably, okay? Let's just kind of delete what I just said. Let's just sit in our comfortable world right here and not go further with any kind of gross, disgusting graphs quite yet. Okay, let's see. Transform, how about this? Transform this equation into a rectangular equation. Okay, and I'm just going to pick this one. Let's say I've picked r equals 4 cos theta plus 4 sine theta. Okay? All right, well, there's many things you could do here, and I should say this, transforming this equation into a rectangular equation, now you know what this means. This just means an equation with rectangular coordinates, as opposed to here, this is a polar equation, an equation in polar coordinates. All right, well, a couple of things. Those ever helpful equations, x squared plus y squared equals r squared, those are fantastic. You also know that r sine theta equals y, and r cos theta equals x. So maybe this is your first time doing this and you say, okay, well, I see that r here, so maybe I can call this, the square root of x squared plus y squared, right? Equals, 4 cos theta. Well, I guess I can do this. 4 times, cos theta will equal x over r, right? So 4 times x over r plus, Oh, 4 times, well, sine theta is y over r. Oh, and can I end here? No, I can't. I don't have only rectangular coordinates. I have an r here. Well, let's see. What if I multiply both sides by r? I'll have r times the root of x squared plus y squared equals 4x plus 4y. And what's going on over here? Well, r is just the square root of x squared plus y squared, so this whole left side just becomes x squared plus y squared equals 4x plus 4y. And technically, this equation's, the directions were transform the equation to a rectangular equation. This is definitely a rectangular equation. Okay, and maybe you identified this curve from your work with Math 2. This is actually a circle. I'll talk about circles in a little bit, just very, very lightly, nothing too scary, okay? But that's an example of just kind of, working with rectangular and polar coordinates and shifting back and forth. Why don't we go ahead and do the reverse? Why don't we say you go ahead and convert this equation now? Okay, convert x squared plus y squared plus 4x. So converse x squared plus y squared plus 4x equals 0 into a polar equation. All right, well, go ahead. You can try it on your own, then replay me. I'm just going to do it right now. If you want to pause me, you certainly could, and then try on your own. And this is where, as you do these more and more, you get a little bit more swift, and you get a little better at this. And you can see some ways you can do this more efficiently, some ways that you wouldn't. But one thing I immediately see here is that I have the x squared plus y squared together. X squared plus y squared I know already equals r squared plus 4 times, okay, x right here. I know x is r cos theta. So r squared plus 4r cos theta equals 0. And there I am. And that's it. I've got an equation in polar coordinates. All right. All right, everyone. So I think you're in a great place. That's it. That's it. This is just very basic, comfortable, introductory polar coordinate systems, introducing you to the polar graph paper, doing a little conversion. And your homework in the text is going to be the following. Okay, here it is. This is the screencast homework, and I will see you on Monday. Goodbye.